Hello there, everyone. We're going to talk nullines, equilibria, Jacobians, and behavior in phase plane dynamics for nonlinear systems. All sorts of good stuff. Really, this is a review of all the things that we've done with nonlinear dynamical systems over the course of the last several weeks. So what I have for you is this particular nonlinear system. Here we go. So I got dx dt equals half x times 1 minus x over 3 minus xy over 4, and something kind of similar-ish for dy dt. Think of this as a predator-prey type model. That's kind of the inspiration that I chose. So let's get going. Nullines. Nullines are the equations that arise when I take dx dt equaling 0. Those are going to be the x nullines. And comparably, when I take dy dt equals 0, those are going to be the y nullines. Okay, so the x nullines in this particular case, if I take dx dt to be 0, I get 1/2 times x times 1 minus x, oops, that extra parenthesis shouldn't be there, sorry. So 1/2 x, 1 minus x on 3 minus xy over 4 equals 0, which I can factor an x out of, right? Leaving me, I'm going to pull the 1/2 through, 1/2 minus x over 6 minus y over 8 equals 0. Right? Just track through the algebra very carefully there. If I factor this x out of everything, I get a 1/2 times 1, 1/2 times x over 3, right here. And I factor the y out of this, I get an x over, oh my goodness gracious, that 1/2 was not there. I get a y over 4. There we go. Okay, so my x nullines are when x equals 0. There's one of them, because that's one thing that solves this equation. And another thing that solves this equation is when y over 4 equals 1/2 minus x over 6. Right? Just taking this term and moving it to the right-hand side. If you multiply through by 4, zoom in just a little bit there for you. If I multiply everything through by 4, I get a 2 minus 4 over 6, so 2/3 x is equal to y. So there's my other nullline. So I've got one nullline that is x equals 0, so that's a vertical line. And I've got another one that's kind of in classic mx plus b form. Okay, for the y nullines, we're going to play the same game. I've got minus y squared over 8 plus xy over 2 equals 0. I can factor out a y, which leaves me negative y over 8 plus x over 2 equals 0. So my y nullines are y equals 0. That's one thing that solves this equation. And doing the algebra kind of all, or fewer steps here. Move this over, I got y over 8 equals x over 2. So that is y equals 4x, so there's the other nullline. So in other words, what I get is I get these collection of equations, and on these two equations, that's where my change in the x direction is 0. So on these, my change is only vertical. And on these two equations, my change in the y direction is 0, so my change is only horizontal. Well, let's take a look at what this looks like in MATLAB. So I've got some MATLAB code over here. Let's let Citrix catch up to us. Okay, so what I've done, I'll walk you through very briefly on the MATLAB code. All right, we've done this before. So I've got some symbolic variables that have the right-hand side is my differential equations. And if I just do an easy plot of the nullline, right, that automatically says, hey, I'm going to take this thing equal to 0 and plot it, and bada bing, bada boom, here we go. There's our two nullines. Now you'll notice that there's more than two. You can see this one here, you can see this one here. So you can see a couple of different things. It splits us into several different regions. And if I'm thinking about this as a predator-prey problem, everything's positive, or at least non-negative. So I'm looking at the first quadrant. So I've got 1, 2, 3, 4 regions. And where the null lines intersect, I get equilibrium points. So I get equilibrium points here. I get one at 0, 0, right? That wouldn't be when these two intersect each other. And when this one and this one intersect each other, so y equals 0 and this particular curve, well, okay, that's down here. I get another equilibrium. And over here, I get another equilibrium. So it looks like I've got 4 equilibria there. And now I can do a few more things analytically before I even look at solutions. So let's go get the equilibria. All right, the equilibria are when simultaneously dx dt and dy dt equals 0. Right, now that is a okay, so when these equal 0, that's spelled incorrectly. Yeah, whatever. Sorry. When these both equal 0, we're looking at the intersections of these things. So I can have MATLAB do the work, or really, I could actually just do the algebra. It's not so hard, but let's let MATLAB do it for us here. So my equilibria are, I'm going to solve when F1 and F2 simultaneously equal 0. I'm going to solve that for X and Y. Right, now remember that MATLAB gives me some structures out. Here, let's make this big full screen. We'll let MATLAB catch up to me. Okay, MATLAB gives me structures out, which is maybe a little bit hard to read. So if I just want the X equilibria and the Y equilibria, and I want them side by side, I'm going to create them as a vector side by side and just spit those guys out. Well, here we are. We got 0, 0, 3, 0, and 3/7, 12/7. So I'm going to write that down on my scratch paper so I remember it. 3/7, 12/7 is my equilibrium point. So I know that right here I've got an equilibrium. Right here I've got an equilibrium. And okay, the others. Now I can do a little bit more. Let's take a look at this interesting one. Let's go get the Jacobian. Okay, so back to side by side again. The Jacobian is a matrix that tells you how this thing behaves near the equilibrium point. So what I'm going to do is I'm going to take the derivative of f1 with respect to x and y. Then I'm going to take f2 with respect to x and y. And then I'm going to evaluate that at my equilibrium point. And that the eigenstructure of this near the equilibrium tell me all of the information about how that equilibrium behaves. Is it a source? Is it a sink? Is it a spiral in? Is it a spiral out? Et cetera, et cetera. Okay, so let's go get that in MATLAB here. So I'm going to build, so again, full screen. So I'm going to build my Jacobian. My Jacobian is a matrix. It is derivative of f1 with x, f1 with y, derivative of f2 with x, f2 with y. Okay, now I can look at it, but it's not going to tell me much. It's just this matrix of functions. I'm just letting MATLAB do all the differentiation for me. That's fine. But the interesting thing now is let's evaluate that at our equilibrium points. 3/7 and 12/7 was one of our equilibrium points. All right, I'll just call that Jacobian for right. Oops, that's not what I meant to do. Okay, so if I call that my Jacobian, ooh, I didn't tell it that it was a function of x and y. Oops, there we go. Okay, so I've got this Jacobian, that's totally fine. Let's maybe turn it into a double precision. So it's actually decimals and not symbols anymore. So there's my Jacobian matrix, but the really interesting thing is the eigenvalues. Okay, now my eigenvalues come out to be complex with negative real parts. So what I know fully well is I'm going to get things that spiral in towards this solution, right? I have an exponentially decaying real part, and I have an oscillator coming from the imaginary part. So I'm going to get spirals that come in. Comparably, I can look at what happens at, say, 0, 0. Now, 0, 0, I've got a 0 eigenvalue and a positive eigenvalue. So that's going to go out. That's going to be a source, right? 3, 0, I think, was one of our equilibria. That guy looks like he's a saddle, right? And I think 0, 2 was the other one. I don't remember. Let's look. 0, 2, that guy looks like he might be, oh, he's got a 0 there. He's a little bit weird. And actually, he didn't show up in our list here either. Yeah, 0, 2 is going to take more analysis, but he's not actually the interesting one here. The interesting guy is our 3 sevenths, 12 sevenths. Okay, so we know what's going to happen there. Now let's go back to doing our by hand analysis. Okay, I'm going to transcribe my differential equation onto a new page. So I've got dx dt is 1/2 x, 1 minus x over 3 minus xy over 4. And dy dt is a similar sort of predator-prey type model. Okay, now what I'm interested in is what happens inside these regions of the phase plane. So for example, if I pick the point 1, 1, so if I say at the point 1, 1, I want to know what's happening. Well, I can look at dx dt and just literally put in 1, 1. So let's say that's a half times 1, so a half. Let's see, 1 minus a third, so that's 2/3, minus 1 times 1 over 4, so that's 1/4. So that is a third minus a fourth, right? So 0.3 minus 0.25, that's a positive number. So what I know out of this is that in this particular case right here, my x direction is saying I'm going to the right. Now if I look at dy dt, right, hold on, this is positive, that's going to the right. Let's think about that. Okay, now my dy dt, let's just plug into this guy. I'm going to plug in 1, 1 because it's a sample point in this region. That gives me minus 1/8 plus 1/2. Well, let's see, negative 1/8 plus a half is also a positive number. So my y direction is positive. And if I put those dudes together, right, I've got something that is going to be up and to the right. So I know fully well that if I plot points in here, they're moving up and to the right. And I'll show you this code in a second. But what we just did is some really simple analysis that shows what's happening in this entire region cut off by the null climbs. Okay, so let's do the same sort of analysis again. Right, I'm going to restart my plot here. That's perfectly okay. Here we go. All right, so maybe let's look at a point that's up in this upper region. So maybe at 2, 2, for example. 2, 2 is right over here. It's up in this upper right-hand region. And I can look at what happens to dx dt. Well, let's see here. That's a 1. That's a 1 minus 2/3, so that's a 1/3. 2, 2 is, let's see, 2 times 2 is 4, so this is a minus 1. So that's 1/3 minus 1, right, which is most definitely a negative number. So what I know is going to happen here is up at 2/3, my x direction is going left. Okay, comparably, dy dt, now I'm plugging into this one. All right, 2, so let's see, 2 is what I'm plugging in, so that's 4/8, so minus a half, plus 2 times 2 is 4, over 2 is 2. All right, well, that's a positive number, so I know that my y direction is positive. So I know that in this particular region, I am going left and up if I put those two vectors together. And again, let's make sure. And there we go. Okay. So again, some really simple analysis tells you what should be happening inside that region. You don't need MATLAB, but I think the MATLAB is a nice way to describe what's actually happening inside those regions, cut off by the null clients. Now, of course, you can do the same thing in all of these regions. So let's restart the plot one more time. And now what I'll do is I'll make this full screen and I'll show you what my code looks like here. This is very similar code to what we've done in the past. But now I'm using the G input function to actually get my initial conditions. That's the graphical input from MATLAB that allows you to use mouse clicks. And let's run it. All right, so down here in the bottom, I know I'm going to go up and right, and sure enough, I do. Top right, I'm going to go left and up, which sure enough, I do. Top left, well, let's see, we haven't done that, but pause and do it. We go down and left in this region. And then over here on the left middle, I've got, again, you can plug in any individual point there to know what it does, but it looks like it goes down and right. And now I know the full dynamics of this system. And furthermore, when I look at this equilibrium point, I am 100% supported by what the eigenstructure says I should be getting in that particular region, which is a spiral in. Negative real part, imaginary parts. The imaginary parts give me the spiral, the negative real part gives me the spiral in. Okay, that's a summary of every single thing that we did for nonlinear dynamical systems. I hope this helps. I hope this brings everything together in one beautiful package for you.